and then you guys can add in what you saw. Or you saw from other people that clicked with you because the answers were made so that like once you submitted yours, you could see other people's, right? So we split the equations into these groups. So we talked about the first group together, right? That the degree of the numerator is higher than the degree of the denominator, okay? And so then we want to talk about, here, I'll make it easier for you guys so you don't have to put people on blast here. So then we went on to talk about looking at the graphs, looking at the number charts, and then talking about answering some questions, seeing if we got them right or wrong, to talk about the end behavior. So what conjecture did you guys make in that group where the degree of the numerator was higher than the degree of the denominator? What was true about the ends of the functions, the end behaviors? Kyla? Okay, that it was either negative infinity or infinity. Did you guys see that pattern there? And we could see it in the pictures of the graphs, right? And we can see it numerically and in the graphs. So in the graphs, we saw that these graphs didn't seem to level out at something. Even this one here, the green one, it might grow a lot slower than some of the other ones, but then when you look at the numbers, that's h of x. You can see with h of x, it's still growing in number, like from 0.3 to 3 to 30. Each time you go further out, it is making a jump. It's not staying around the same number when you move far away. It's going to a new number value, okay? Then in the second group, okay, what was true about the degree of numerator and denominator in this group of equations? Liam? Good. They were equal. They had the same degree in numerator and denominator. So I've given you guys groups of equations, and I split them up by this characteristic about how the relationship is between the degree of the numerator and denominator. Now, when we look at these ones that had the same degree in numerator and denominator, here were some graphs, right? Here were the numerical values, and then you guys went through some multiple choice questions. And what was the conjecture you could come up here? If I have a function whose degree is the same in the numerator as it is in the denominator, what do you think is happening with the end behavior of the function? So if we look at the graphs, were the ends of the graphs going towards infinity or negative infinity? This picture looks a lot different than the other picture, right? I'll zoom out further just to make my point. If you zoom really far out, okay, these colored lines that represent each of the graphs, they look horizontal, right? They don't look like they're going way up or way down, which is much different than what we saw in the first group, okay? So when you guys looked at the end, so let's look at the number values. Let's look at f of x, for example, okay? It did some stuff at the ends. And remember, as you get to these numbers, we were making giant jumps. We were going from like an x of 1 to an x of 10 to like 100 to 1,000. So look at my x value here at f of x. Okay? When I plugged in like 10, I got 2.5. When I plugged in something like 100, I got 2.05. Then I went all the way out to 1,000, and it barely changed. It went from 2.05 to 2.005. So yes, it got smaller, but is it going towards negative infinity? No. If it was going downward like that, even if it was slow, I would at least see it change a number when I move 900 spaces away from it, right? Okay? So this tends to be staying really close to one number no matter how far we move away from it. Okay? What number does it seem to be staying really close to? So if we continued this pattern, we went from 2.5 to 2.05 to 2.005, what would you expect to see further on if I kept trying to plug in things like 10,000, 1 million, something like that? What do you guys think would happen? Jesus? Yeah, so it'd be like 2.00000, and it wouldn't always be 5. That's kind of based on the numbers I chose. But you see that, like, it's staying close to 2, though it is getting smaller. And then look at the other side of it. It went from like 1.45, 1.94, 1.994. I would expect if that pattern continues. Remember, there's like a leap of 900 in there. I moved over 900 spaces, and I went up 0.05. Like, I am not going towards infinity, right? I'm kind of just hovering right around this number. And the number that I'm hovering around here on this side is also 2, okay? And that's why in the graphs, the lines look horizontal. Let's look specifically at f of x. Here's f of x. It looks horizontal, okay? And let's see, that's 20, so that's 10, that's 5. So this is right around 2. It looks like, with my eye, that it's just staying at 2. Okay, it's not. This is a little bit below 2, and it's growing constantly, but never to the point that it will surpass 2. Okay? Is that all right with everybody? So what conjecture can we make about the end behavior? When the numerator and denominator have the same degree, their end behavior does what? It doesn't go towards infinity or negative infinity. What does it do? You don't have to be super specific as you can get, as much as you can tell me. Jenna? It stays around the same number. And we can't say the number, right? One of them it was like 2, one of them it was something else. So we don't know the number, but it stays around some number. Okay, so that's as much as we know now. Then if we look at the third group, okay, so the third group, what was true about the relationship between degree of numerator and degree of denominator? Okay. Good. The degree of the numerator was less than the degree of the denominator. So we kind of split it into these 3 possible categories. If you have a polynomial function in numerator and denominator, either the numerator has higher degree, they have the same degree, or the denominator has the higher degree. Like, those are the only 3 things that could happen. So here's that third section. Okay. Then as we look at these, they look really similar to the last group, right, in behavior. The fact that the ends look horizontal instead of going up towards infinity or negative infinity. Yet, how do these graphs look different from the last group? So I just said they look similar in the fact that their ends are seeming to be horizontal and not shooting up or down on the left and the right. But what seems significantly different when we look at this picture compared to when we looked at the picture before? Jenna? Yeah. So these ones, not only do they stay at some number, but look at them. They all are coming back to the x-axis, right? Whereas before, when you saw the picture, some of them were up here, some of them were down here. They were making horizontal lines, but kind of at different places. These ones are making those horizontal lines, but all at the x-axis. Okay? And when you look at the numbers, you should see the same thing happen. Look at the y values. All the y values, as we go further out, seem to be getting closer and closer to 0. Okay? So not just any number in this case, like we can't tell. These ones all seem to kind of head and hang out at 0 at the ends. Okay? So what would be the conjecture if I lay in front of you an equation where the degree of the denominator is the higher degree? You would expect the ends to do what? You might know nothing else, but you would expect the ends to do what? What did you guys write as your conjecture at the end of this? I can pull them up, but I don't want to put people on the spot when they were just investigating. Okay, so when the degree was bigger in the denominator, what conjecture can we make about end behavior? Jesus? That it will be close to 0. So if somebody writes an equation up for me, and I know nothing about it, but let's say like it just has the higher degree in the denominator. I don't know anything about what this graph looks like, but I know that eventually if you go far enough out, it looks horizontal at 0. Like, that's what I know about it. All just because I can see that higher degree there, which you can see is not going to do the whole thing for us, but is going to be extremely useful for us to know if we're trying to graph it so that we don't have to keep plugging in points forever. We just kind of know like, oh, now the end goes like this once I have some other general features on there. Okay? So we are going to try and summarize like you guys did at the end in the investigation. Now that you've got to visually see it, numerically see what's happening, now we're going to kind of put it together in a more concise pattern. And again, I could have just told you this stuff right at the beginning, but the idea is there's value in you seeing it and experiencing it and thinking about it because this is a lot to memorize. So hopefully that experience makes the memorization a little bit easier because you kind of went through that process. Okay? So if you have your note guide, this is in your note guide. If you don't have your note guide, then wherever you take your notes, you can just write this down. All right, so what you see at the top, if in your note guide, or if you don't have a note guide, you don't need to write down those examples, but this is just the definition of the polynomial and the same pictures we looked at before to remind you that these polynomial functions can have lots of different strange characteristics and look lots of different ways. They can have asymptotes, they can have holes in them, okay? Sometimes they look familiar, sometimes they don't. And so you just found out some really important things. When somebody puts this in front of you, like I said over here, if I look at one example and I see that the degree is higher in the denominator, I immediately know the ends of that function should kind of be around 0. They should be horizontal around 0. Whereas when I look at this function and the higher degree is in the numerator, I don't know where, but I immediately know the ends go up towards infinity or down towards negative infinity because that's what we saw in that case. Okay? So we basically want to summarize those thoughts for you right here. So the degree of the numerator is larger than we're going to do the first one first. If it's larger than the degree of the denominator, I forget. Right around? Yeah. Okay. So if the degree, sorry guys. Apparently wasn't working, now it's working, but I don't remember how to work it. So the degree of the numerator is larger than the degree of the denominator. That was the first group we looked at. Okay. And so an example, just give yourself an example. So I can just write down that one right there. I'm just trying to make sure you guys understand what we're comparing when we say that. Pen is not working. So like 3x squared plus 1 over x minus 2. Anything where the degree of the numerator is higher. We don't have to have the same example. Just trying to make sure you can look back and know what we were talking about. So in these ones, was there a horizontal asymptote? So remember when we learned our reciprocal function, horizontal asymptotes were there because the ends got horizontal instead of going to infinity or negative infinity. Okay? When the numerator was higher, that first group, where did our end behaviors go? Yeah, infinity or negative infinity, right? So is there a horizontal asymptote? Are they following a horizontal line at the end? No. Okay. So then how is the horizontal asymptote found? Well, it's not, okay, because there isn't one. And we're going to make a note for ourselves that instead you follow a different thing. So if you don't follow a horizontal line, there's got to be some other thing you follow. And that's called an oblique asymptote. And we'll talk about how to find those later. It just means it wasn't a horizontal thing. It was some other shape. Maybe it's a parabola. Maybe it's like a line with a slope that it follows towards infinity or negative infinity. And so it's not horizontal. It has a different name called oblique. And then that should tell you you can't have both of these. You can't have a horizontal asymptote and an oblique asymptote because they're there to tell you where the ends go. So either they go horizontal or they don't and they go what we call oblique and follow some other shape. Okay? All right, second group. The degree of the numerator is the same or equal to the degree of the denominator. So that's the second group you looked at. They had the same degree. Okay? An example of that, anything with the same degree. So I could do x plus 2 over x plus 3. Those would have the same degree. I could do 5x plus 2 over 4x plus 3. I could do 5x squared plus 2 over 4x squared plus 3. It doesn't matter. Okay, same degree. Is there a horizontal asymptote? So in the second group, did the ends of the graphs go horizontal? Yeah, they stayed at one number instead of going to infinity or negative infinity. And then we're going to come back to then how do we find it? Because remember, that one was a little vague, right? We said they were all at a number, but those ones were all at different numbers, and so we want to try and establish a way to find that number without doing the chart or making the graph, because we're supposed to be using this information to make the graph, so we wouldn't have the graph yet, okay? So there's got to be a way for us to have some idea of what's happening without plugging in a million numbers and already having the graph in front of us, okay? And then the last situation was that the degree of the numerator is smaller or less than the degree of the denominator, okay? So something like this, where you have the larger degree in the denominator, okay? And did those graphs end with horizontal ends? They did, right? And those graphs were a little more specific than the group 2, right? Group 2, our conjecture was they ended at some number, but we couldn't really tell you which one. But then when we looked at the picture for group 3 and we looked at the numbers, those ones didn't just end at some number horizontally. Where were they at? 0. So you immediately know in this situation that the ends should end at 0, meaning you automatically already have the equation for the horizontal asymptote. They have to follow the horizontal line at 0. That equation is y equals 0. You don't have to find it. You should just know it if you know that you're in that situation, okay? So the main question becomes, how do we find the asymptotes when the degree of the numerator is the same as the degree of the denominator? Like, how do we figure that out? We know it's y equals, and it's some number, and that the number can change. But the question is, can I establish some pattern that finds that number? So I'm going to go back to our investigation one more time. We're going to look at each of those and which number they ended up at, and if that has any relationship to the equation, because that's what we would have in front of us. And if we can look at an equation and immediately know it versus having to plug in a bunch of numbers to try and figure it out, okay? So when I go back to our investigation, and we look at group 2. All right, so let's look at f of x first. Okay, here it is. So this was f of x. We already looked at this specifically, and we said the asymptote was at 2. Okay? Look at the equation for f of x. Okay? Is there anything there, okay, that would tell you that your asymptote is at 2? Okay? I'm going to look at another one, too. Let's look at h of x, or g of x. Here's g of x, okay? Kind of looks close to 0. I'm going to go to the numbers real quick. For g of x, it seems to be around 0.2. Okay? What is 0.2 as a fraction? 1/5. Okay? So g of x, look at the equation for g of x. Its horizontal asymptote seems to be at 1/5. So for f of x, it seems to be at 2. For g of x, it seems to be at 1/5. I'm going to go to j of x, and I'll come back to the other. So j of x, again, we're kind of zoomed out. I'm going to look at the numbers. J of x seems to go to 4. Okay? So j of x has an asymptote at 4. Okay? And then the last one we're going to look at, h of x, again seems close to 0, but I'm going to look at the numbers. It seems to be going to like a 0.3 repeating, which is like what as a fraction? 1/3, a negative 1/3, okay? And so it seems to be negative 1/3. So again, look at the equations. First equation, f of x, 2 ended up being the asymptote, okay? Second equation, g of x, 1/5 ended up being the asymptote, okay? Third equation, h of x, negative 1/3 ended up being the asymptote, okay? And fourth equation, j of x, 4 ended up being where the asymptote is. Jesus? Yeah, I mean, a rational function is essentially a division problem, right? And there's a lot going on in these divisions problems, but when you think about it, when you go really far in the equation and you're plugging in really big numbers, these ones with the big powers, if I take 1,000 and cube it, like this minus 10 is almost doing nothing at that point because I've made such a large number that minus 10 does matter, but like it doesn't really matter that much. So when you go way out to the ends, it's really just the highest powers that are kind of controlling what's happening to the graph. So it's almost like you can say, I know this stuff is here, but like with really big numbers, millions, billions, whatever, these don't make a big difference once I cube a billion, you know, like these other things pale in comparison. So I'm really just looking here, what's the relationship between 8x cubed and 2x cubed in a fraction like that? 8x cubed divided by 2x cubed is 4. And that's why the asymptote is ending at 4, because when you plug in really big numbers, these things stop mattering, which means these are pulling all the weight, calculating most of the number, and they're getting really close to 4. Why they don't actually equal 4 like they do? Because of these little teeny parts over here that you're seeing, okay? That 4.00006 or something is coming from those other things, all right? So if you look at h of x, you can see highest power, negative 3x squared over 9x squared. That's where you'd get your negative 1/3. G of x, x squared over 5x squared is where we'd get our 1/5. And for f of x, 12x over 6x is where we'd get our 2. Is that all right with everybody? So we're really just looking at those lead coefficients if you wrote it in standard form, and that should give you where your asymptote is. And so even when it's at another number, we can easily figure it out, okay? So just go back and make a note for yourself in here about how to find your horizontal asymptote when they have the same degree, the second situation, that you want to use the lead coefficients, okay? So what we mean by that, we want to use the lead coefficients. So when we have here, I don't know, 3x squared minus 2 over 5x squared plus 1, I'm looking right here. This would tell me, first I'd look here and see they're the same degree, so I know they do go horizontal, right, at a specific number. And then I look here to determine what that number would be, and in this case it would be 3/5. Okay? So what we've established with this investigation is we basically have established that when we get a crazy equation like this, we can at least look at the degrees of the numerator and denominator and compare them, and it can tell us what's happening at the ends of the function. So the other things that we would want is like, where is it being split up into different branches? Where is it going like above or below the axis so I know where to sketch it? And so we're going to work on finding those things as well, okay? But we're not going to do that today. So today we're just establishing end behavior of our function. Okay? And that end behavior can now be at a number. It was in these two cases that have horizontal asymptotes. Okay? And that number can be determined by the lead coefficients. Here it was automatically 0. And side note of that, kind of like what we talked before. Let's say you had this. So the degree is higher in the denominator, so I know it's automatically 0 because I've memorized that or whatever. But just like we talked about before, when you plug in really, really, really big numbers, this, like other parts, start to not matter. So it's really like having x over x squared. If you had x over x squared, how would that simplify? If I had x over x squared, what would that simplify to be? 1 over x. And if you plug in really big numbers to 1 over x, what kind of number are you getting as you start plugging really big numbers in for x? Really small numbers that are closer and closer to 0, which is why our asymptote is at 0 all the time. Whereas in these ones, where you have a higher degree in the numerator, okay, again, as I plug in larger and larger numbers, these other pieces start to not matter as much as the highest powers. If I looked just at the highest powers, x cubed over 2x, the x's would all get canceled out no matter how much bigger the numerator was. It's going to cancel all the denominator out if it has the higher degree, right? So then you're left with x's in the numerator, whereas I start plugging bigger and bigger numbers in here, it's going to get just really big, right? And that's why you're seeing the behavior here not have a horizontal asymptote and go towards infinity or negative infinity, because your bigger powers are up here, your bigger numbers up here, or your more negative numbers, which makes it go way down towards negative infinity. So you're just getting gigantic stuff. Whereas here, they're canceling each other out. And here, the big stuff is in the denominator, which overall is making it really tiny stuff that's close to zero, okay? So hopefully between the investigation and what we talked about today, this is one of the harder things just because there's a lot of cases just to figure out the end behavior and if there's a horizontal asymptote. And then tomorrow we'll talk about like vertical asymptotes, intercepts, like how would we find all these other things to try and help us get a sketch of the graph, okay? Is that all right with everybody? Okay. So I'm going to check on Canvas your due dates because I think allowing you guys